Yeah, my name's Adam Laurie, also known as RF Idiot, also known as Major Malfunction, if you ever come to DEF CON. And I'm an open source researcher, been in the security business for 20, 30 years. So I'm kind of old school. And one of the things I like to do is look at new technologies. And when I first started looking at RFID, it was very new. There were no tools around, and so we had to develop our own tool sets. So today I'm talking about that development process and you know what we need to do to get started when a new technology comes along. I don't have any slides. I've just got some GitHub repos which you'll find useful if you want to get into this, and some of the websites I'll go to actually show some illustrations of what I'm talking about. So I'll take you through the kind of process of evolution. So we'll talk a little bit about standard RFID, but I'm also going to talk about the difference with UHF RFID. And the reason it was particularly interesting for me, and I'm surprised it hasn't produced more discussion yet, and I'm hoping this will maybe help to kickstart that process. Haven't really seen any tools around for UHF RFID. But one of the things that comes up a lot when you talk about RFID is what range can I attack someone from? And with traditional RFID, I mean, the first thing to say is RFID as a term for this technology is a misnomer. Most things that are referred to as RFID are not actually using radio. So RFID stands for radio frequency identification, but with most RFID systems that you encounter on a daily basis, there's no radio involved whatsoever. It's actually using near-field communications, which is inductively coupled, basically. So better known as NFC, that's the correct terminology. You'll hear them used interchangeably, but they're really not interchangeable. So UHF RFID is genuine. Sorry, I thought someone was shouting a question from the back. UHF RFID is genuine radio RFID. Okay, so first of all, as I said, when I first started looking at RFID, there were no real tools around. So RF Idiot was the first application that I created. And this is an open source Python software library. You can download it from GitHub. It's been around a fairly long time. It doesn't change much because it basically does what it says on the tin. There's not much to add really these days. I mean, I might start going and updating it for some of the MyFair exploits and stuff, but they've been done elsewhere, so there's little point. But a lot of researchers do use it as the basis for their attack tools. So if you go and look at a lot of the published work that's been doing practical application, and that's what it was designed for. It was designed to make things easy to go and start attacking and researching weaknesses in RFID. And I'm happy to say a lot of people have used it for that basis, but it's just an underlying library. It abstracts the hardware and the tags for you and just lets you do stuff to tags. My next foray into the RFID world was actually to combine the software and the hardware. So I don't know if any of you saw the talk a couple of talks ago about software-defined radio, but basically software-defined radio uses the power of modern computers to do most of the logic and the processing for you once you've captured the radio signal. So you have an analog circuit that captures the radio from the airwaves, turns it into digital form, and you do the rest in digital form. And I thought about, well, why can't we do the same for RFID? And so I applied the principles of software-defined radio to RFID. And with my partner, Zach Franken, at the time, he designed the hardware and I wrote the firmware, and we built this device called RFiddler. And our Fiddler is basically a low-frequency software-defined RFID reader. And again, fully open source. You can download the software from GitHub. You can also download the hardware design. And if you want to build the circuit yourself, send the bombs to your favorite manufacturer and he can churn out a circuit. There are still a few available in production if you contact me. We've stopped building them, but there's a few left if anyone wants one. So just give me a shout. High frequency. So basically in the world of RFID, there's two worlds, I guess. There's a low frequency and a high frequency. And the early stuff was low frequency, which is 125 kilohertz, 134 125/134 kilohertz. High frequency is 1356 megahertz. And most of that these days is done with off-the-shelf commercial readers. You don't need to bother building dedicated hardware to do most of the attacks that exist today for NFC. There's a very good library called NFC Tools, and part of it is libNFC, and then there's various attack tools within it like MFOC and MFC UK, My Lazy Cracker, and so on, that will do all the stuff that you've read about, so MyFair hacks, cloning hotel keys and all that kind of stuff. I'm also a contributor to that. Have been for many years. So I tend to add things to that rather than reinvent the wheel again somewhere else. So if you do want to get down and dirty with RFID/NFC, the hardware kind of Swiss Army knife is the Proxmark 3. Proxmark 3 was built many, many years ago, kind of bumbled along for a while, had lots of issues, hardware and software. Recently, it's seen a big revival. I mean, NFC has become really important in the modern world, so it's been kind of revived by these guys. So Iceman is the main software contributor these days. So when you're looking for the latest Proxmark 3 information, I would definitely go to Iceman. To be honest, I'm not sure which one of his forks is the one to go for, because there's the RFID research group and then there's the Iceman fork. And yeah, you need to talk to him and look at the text to see which one is the one for you. But if you're buying hardware from, say, ProxGrind, then you probably want the RFID research group stuff. So a little bit about nuts and bolts. So this is our Fiddler, which is the hardware that we built. And if I scroll down a bit, we can start talking about how it works. So the way RFID works, or NFC works, is your reader has a coil, it generates energy. When you place the tag into the reader field, the tag gets energized. It steals some energy from that coil, basically. And then the two devices can talk to each other. So this is an oscilloscope trace of 125 kilohertz carrier signal, and a carrier signal is literally just, you take the coil, you energize it a certain number of times per second, and that's your frequency. So by energize, I mean you give it 5 volts and you take it away again. So that up-down pattern on there is me giving that coil 5 volts 125,000 times a second, and that generates 125 kilohertz carrier. If I want to talk to the tag, I can just stop sending carrier. So for a very brief period, the voltage will drop. The tag itself has a capacitor on it, so it's taken some power and it's charged the capacitor up, so the chip that on the tag will keep running even though it's lost power, as long as you don't lose it for too long. So the capacitor will get you over that hump, and so the reader can talk to the tag. In this case, it's sending long, long, short, short, short. So that's a little binary message. You could read that as 11000. Similarly, if the tag creates a voltage drop on its own coil, the reader will detect that because it can measure its own voltage. So in this case, we can see the carrier has been affected by the tag grounding its coil. So here we see a dip in voltage because the tag has sent a message back. And in this case, again, you could think of these as ones and noughts. So if we say a dip is a 0 and a high is a 1, that would be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, etc. So the tag and the reader can talk to each other. So that's the fundamentals how it works. This is the actual work that I'm talking about today. So this is when we switch to UHF. Now in UHF, RFID, things work differently, as I say. So instead of being inductively coupled, you're using actual real radio. So if you want to actually see what one of these tags looks like, come up to me after the talk and I'll show you. But you may have seen one either in shops, or some luggage tags have them. Basically what you'll see is an arrangement where you've got a sort of antennas coming out on both sides of the tag and maybe a big ground plane on the end. So it looks like a kind of spider on either side of the label. And basically what happens is the radio, similarly to the inductive coupling, where when you put two coils together, one takes the energy from the other. In RF, if you send a signal to a receiving antenna and the signal flows through that antenna, it will generate a signal as well. So you'll get a very small amount of radiated signal back from that antenna, and that's called backscatter. If you ground the antenna, and I always get this the wrong way around, in one state it reflects and in the other it doesn't. So the receiving chip can modulate that signal, and it can either choose to send backscatter or not. So in exactly the same way that the NFC tag can modulate the coil, an RF tag can modulate its antenna and backscatter or not. So this project was based on an existing research project. As I say, what I'm trying to do is kickstart something because I haven't seen anyone really working in this field. So I'm trying to create a repo of working software that's easy to use, and we can start adding features to it. So if you want to get involved, again, this is on GitHub. Just go to my repo and look at GEN2 UHF RFID reader. So what I hope I'm going to do now is an actual demo. And that's always a bad idea, as you know. So a couple of things, lessons I learned while building. In order to do this, you need a very fast SDR. So the original project was done using a USRP, which is quite pricey. I'm using a BladeRF. There's no reason you shouldn't be able to convert it to some others. There are some software-defined radios that probably will never work. So things like HACRF, which is half duplex, so you can either transmit or receive. You can't do both. The timings on this is very, very critical. So you have to be able to receive and send at the same time, because you'll never be able to switch between transmit and receive fast enough. So I use the BladeRF because it's full duplex. It's about half the cost of a USRP, probably even less than that. A couple of major lessons I learned there. One is, for some reason, under Linux, certainly under Ubuntu, they're still using libbladerf 1, which is the first version of the BladeRF library. And there's some really horrible bugs in there. I mean, basically, the way a BladeRF works is it has 3 stages of amplification. And when you set your amplitude in your Python GNU radio software, the libbladerf library handles that for you. In libbladerf 1, it seems to be somewhat random. So you can spend like days or weeks changing parameters, trying to figure out why it's not working. Suddenly it will start working and you're like, hallelujah, I found it. And then you switch it all off, come back the next day and nothing's working again and you're back to square one. And the reason in the end turned out to be that some of those stages only get set at certain levels. So if you set your amplitude to like way maximum, then things in the middle get set. When you bring it back down, they don't get unset. So you end up with magically some formula that works, but you don't know how you got there because you've been experimenting. So make sure, if you want to try this, you're using LibBladeRF 2. Make sure LibBladeRF 1 doesn't even exist on your system when you build the software, or you're in for a world of pain. I spent 6 weeks banging my head against a brick wall before I figured that one out. So the other thing is tuning your antenna is very important. So you'll see I did a quick test run here, and we're not getting any response from the tag. So basically what this software is doing is, so I didn't mean to do that. Let me just run that again. It's all a bit mysterious. When you run it, you know, stuff's going on in the background. The radio's sending a signal. It may be getting some backscatter, it may not. So what I found was you can use tools like MATLAB or Octave or whatever. So I've got an Octave script here. If I run this, this will show us a dump of the signal that we're receiving. So here we can see that is an old signal. Okay. We don't have a huge amount of time, so I'll show you an old signal. So these really big spikes are my commands going out, and these smaller ones are the replies from the tag. So the way UHF works is you send a query command, and then within a random space of time, any tags in the field will respond with a random number. If you echo that random number back to the tag, it will then respond with its ID. And again, one of the things I found that was super critical was the timing gap. So when the tag sends you the random number, you have to respond with your acknowledgement within a really, really, really critical time period. And the reason that I've looked at this project, and there's a lot of forks of it, and you can see people clearly trying to get this working. And it looks like from what they're doing and the additions they're making to the code, they went down the same path I did, which was, well, I've got the radio working and I can see the tag sending me this random number, but it never responds when I send the command. So maybe I'm getting the random number wrong, or I'm filtering wrong. So I started changing the filters to like band pass or low pass, whatever, trying to get a better signal. And I never got a response. But in 6 weeks, 1 or 2 times I got a response. So I'm like, okay, sometimes the stars align and it all works, and I don't know why. And in the end, it turned out that this gap here, this timing gap, is super, super critical. And actually, if you go way back to the original project that this research is based on, there's a note from the author saying he had to rewrite the GNU radio USB handling routines to take out all the USB buffering so it ran in nearly real time in order to get this gap right. And as soon as I saw that, I looked at LibBladeRF, and there's this magic, well, you can just set the number of buffers to 2, I think, is the minimum. And I did that, and bingo, it just worked. And it was like, hallelujah, 6 weeks of, well, there was the previous 6 weeks with the other banging my head against a brick wall. But and the final magic sauce was to tune your antenna. So if I quickly tune my antenna, I'm hoping we'll actually get a read. So you run BladeRF CLI in interactive mode. So you've got two calibration commands you have to, or three. You calibrate the amps, and then you cal DC RX. And this is calibrating the DC offsets, and TX. So you need to do this once every time you change the amplitude or the frequency. And then with any luck, no, typical. It does also need to warm up. It's going to be one of those demos where I never get a real... And I'll get back to the speaker ready room and it'll all just work perfectly. Let's try again. So I'm going to leave that running for a couple of seconds. Are there any questions? Because it does actually genuinely make a difference if the whole circuit warms up. It will change the frequency response and so on. So if we have quick questions, and then I'll try and do a final finishing mic drop demo. Any questions?
There are no questions.
So, yeah, look at that. So just letting it warm up. Can you put my screen back on a second? So yeah, having let the circuit warm up, we now actually see the correctly received signal has been interpreted, and there's our ID. One of the other things I did, and actually we can probably see that better in the... Where is it? I hate touchpads. So my screenshot's gone. Okay, this is weird. This is an old version. There we go. So when I looked at the project, basically all the code does a very basic, here's the request, here's the tag random number, this is me acknowledging it, and this is the final EPC code being sent. I've started to add new commands as well. So what you can do is you can actually use a select command. So you create a mask of which tags you want to respond. So the way the EPC codes work is they have encoded in them the manufacturer or the purpose of the tag or whatever. So if you want to go scanning for particular tag types, you can now set this mask and only the right kind of tag will respond. So if you wanted to do a long-range scanner, say I want to see if there's any of these type of tags in the room, you should be able to sweep the room, and if you get any response, that's one of those. Okay, so there you go. Demo worked. Thank the demo gods. Any questions?
Have you looked into power amplifiers to extend the range?
Yeah, so so the question was, have we looked at amplifiers to extend the range? So one of the precautions that I take is I use a thing called a circulator. So this guy in the middle, so here's my antenna, and you can see I've only got one antenna. I don't have a transmit and receive. The reason being, if you have a transmit and receive antenna and you crank up the amplification, you can very easily blow your receive circuit. So the nice thing about a circulator is the signal you send will not come back full strength into the receiver. So, yes, you could take one of those and you could stick an amp in. I mean, the original project with the USRP claimed a range of about 6 meters. The most I've got working without an amp is about 1 meter, but that's on the BladeRF, not I assume the USRP is much higher power. I've got an amp, but I haven't tried it yet. But I imagine there's no reason you shouldn't be able to just keep extending that range. I don't know what the limit will be, but again, with these plots, it'll be very easy to tune that and see at what point your backscatter disappears in the noise.
Any other questions from the audience? Then we can move on to the slide now.
Can we use a smartphone which has an NFC general reader? Yeah, you can use a smartphone for doing most of the MyFair NFC stuff. There is a MyFair tool. I think it might even be called MyFair tool, which will work with the Chinese magic cards and do card cloning and all the sort of standard attacks. I'm not sure if all the attacks like DarkSide and so on have been, I think they might have been actually added to it. So, you can definitely use your NFC. You can also, actually there is a shim to use an Android NFC reader with the RF Idiot library that I wrote. I don't know if there's one for libNFC, but it wouldn't be hard to do. So, what is the coolest hack you've ever seen which uses this type of attack? I think I have to revert to the standard answer is I could tell you, but then I'd have to kill you. So,
have any more questions arisen from the audience itself? No? Then I'd like you all to give a big hand to Adam Laurie, RF Idiot.
Thank you.